and specifically in...
Well, you already gave a good introduction to this talk. So yeah, welcome everyone to my presentation on accelerating the network for deep learning at scale. And before I start, just a very brief disclaimer, like I'm a researcher at Nvidia, so I don't directly work on products or current technologies, so just keep that in mind when we go through this presentation. It will be mostly about the research we're doing. And as it was already hinted at, this is the graph I want to start with, and basically Sylvain and I already explained that. I want to show this just because to make clear that why we need all this compute, right? Why do we need a scale? And it basically starts with this graph, which was a study done by OpenAI and I believe Stanford. We looked at the computational requirements to train neural networks, right? And they went back to like 1960, where the perceptron appeared first. And then people were doing neural networks until 2012, and it basically followed Moore's law, right? So this was our contract between industry and supply side, demand side. Let me get a laser pointer. Okay. But then 2012, AlexNet came along, which was one of the first, or was the first network that basically used GPUs as an accelerator, and with great success, right? So since then, people came up with great networks, large networks, and they're computationally demanding. So on average, you can say that the demand doubles every 3 to 4 months. So this is a lot. The slope is a lot steeper than Moore's law, for example. The second thing I want to highlight is that models are getting really, really large. And they're getting large very, very fast. So especially in the area of natural language processing, which is what this graph shows here, the models double about every 2 to 3 months. So I'm not saying this will go on forever, right? But this is the trajectory we are on right now. So 2018, OpenAI released GPT, which back then was a really breakthrough in natural language processing. A couple months later, GPT-2 already had like a lot more parameters, right? From 100 million to 1.5 billion. And then this year, GPT-3 came out with like 175 billion. And I'm sure somewhere in OpenAI or Microsoft or anywhere else, someone's already building larger models. So I believe this will probably go on for a little longer. So yeah, within 2 years, you basically get a 1,500x increase in model size. So this is really astonishing. So this is the demand side. We can also look a little bit at the supply side, right? And in particular, GPUs. For example, 2016, Pascal GPU was released. Had about like 20 teraflops of performance, half precision. A year later, Volta came out with tensor cores, which improved the performance greatly, right? So this year, Ampere came out, and not only the tensor cores were greatly improved, we added another specialization, right? We added support for sparse data, which again boosted the performance a lot more. So if you look at the numbers, you can basically say, okay, performance doubles roughly every 10 months, right? Of course, we don't release a new chip every 10 months, but roughly every 10 months we get double performance. And that's just hardware, right? There's also software. So this looks at 3 different versions of MLPerf. I believe there's like 1.5 years between the first and the third one. You can see it's the same network trained on the same hardware, but we still get substantial speedups, right? So there's a lot of optimization on the software side that is being done, and there's still more to be done, right? So people do program these neural networks in Python, right? So Python is a great language, but it's not always the most efficient, right? People come up with faster backends written in C and C++, which improves the performance further. So we can see that the demand for compute and memory goes up. We already build great chips, and they're fast, but they're not quite enough, right? So on the right side, if you basically take these ratios, like, okay, compute doubles every 3 to 4 months, performance doubles every 10 months, you can see, like, if we look out like 2 years from now, right? I mean, it's just a very naive projection here. You can see like we're about like 16x off, right? what we can supply and what the demand is. So it's clear that we need a network, we need a scale to fill in that gap. So for the rest of the talk, right, I want to give you a very brief overview of today's system. So what are we training on today? And then show you the communication patterns in DL training, like how do we scale, how do we communicate? And then dive into some research we've been doing, basically moving some of the acceleration into the network. Okay, today's system. So today's system, it starts with a GPU. This is basically Nvidia's core product, right? The GPU architecture, it's the same architecture you have in your gaming PC at home. It's the same architecture that is used in robotics and cars. And the same architecture is used for data center GPUs, right? It's just scaled differently. So we start with a GPU, but as you saw, right, a single GPU is not nearly enough to do these training jobs. So we scale it up. We build a big node with 8 of these GPUs in there. We add high-speed NVLink, which is our high bandwidth interconnect. And then we get this DGX box, right? And then you can see like it has 65,000 CUDA cores, right? Which is basically the ALU in the GPU. But this is also not enough, right? So we need to scale out. And the way we do it is basically we build these superpods. This is a reference design. You can download it from Nvidia. It basically tells you, okay, you buy a bunch of these boxes, you buy networking gear, and then you hook it up, right? And then you get this superpod. And it uses InfiniBand as the interconnect, so like very high bandwidth, low latency. And you get a really, really big GPU. Let's look at the back of such a system, right? So this is basically the back plane of a DGX box. Inside, it's a lot of compute. And what you can see in the back, there are a lot of ports where you can stick in a networking cable. There's storage, there's management, there's like 8 NICs, 8 InfiniBand HDR NICs that would deliver like 400 gigabytes of bidirectional bandwidth together, right? There's a lot of bandwidth in these systems. Inside, we have the GPU with NVLink connected, which is 600 gigabytes per GPU. And then we add 6 of these switches basically to create a full bisection bandwidth non-blocking interconnect. So all the GPUs can talk to each other. It's just loads and stores. It's a shared memory interconnect. So this is the building block for these large clusters for the superpod. So once you put the superpod together, you get a really nice supercomputer, right? And this one is Selene. It's hosted in Santa Clara. It's basically built upon the superpod reference design. And it's the #1 on MLPerf for commercially available systems and the 7th fastest computer in the world. So that itself is cool. But what's also really astonishing is it was built and assembled in 3 weeks during a pandemic. So they had like only a couple of guys in the data center putting these systems together. But within 3 weeks, they were able to turn it on and run jobs, right? So the software comes with it. And you can see like in 4 years of MLPerf, we can show that we improve performance up to 4x, right? For some of the workloads like translation. Image classification doesn't, it's only 2x, but we can get up to 4x. And that's a great speed up, right? And MLPerf are not the largest networks, right? There are others like GPT-3 or something like that, right? And they are not in MLPerf. So they would require even larger systems, for example. All right, so that's today's system. So I don't want to give a marketing presentation. So let's go into the communication patterns. So if you want to scale out training, right, you have 2 choices. You have data parallel or model parallel. Well, I guess you have 3, you have hybrid. And I just want to briefly introduce them to you. So it starts with a training set. So a training set is samples and labels, for example, images, and that image shows a cat. And then you batch it, right? You take samples out of the training set and you batch it. If you had a single GPU run, you would take this batch, run it on a GPU, compute all those parameter updates in your model, and then go to the next batch, right? In data parallel training, we divide this batch further. We divide it into sub-batches. So each sub-batch runs on a GPU. Every GPU runs a replica of the model. And then it calculates the weight gradients for its input batch, right? So the rate gradients are basically telling you how much you need to tweak every parameter to reduce the loss function. And with that rate gradient, you do an all reduce, for example, because everyone needs to share what they learned. And once you have the reduced rate gradient, you update your rates, and then you go back, take the next batch out of the training set. And once you're done with the training set, that's one epoch, but usually you train for multiple epochs. So there are three phases. It's compute, which is basically given by the sub-batch size and the model size. The R-reduce and the optimizer both only depend on the model size. So it doesn't really matter how many samples you process per GPU. And for the communication pattern, you need to reduce the rate gradients. So there's generally like two approaches. I don't want to go into detail of the left one. It's a parameter server. So you have the rate stored somewhere. You send the rate gradient, the server runs the optimizer, and you get the rates back. The right approach is basically an all reduce, right? Like an MPI. Every worker basically reduces the rate gradient together with the other workers directly. There's no special place where the rates are stored, like in the left-hand side. All right, the second approach is model parallelism. So as the name suggests, instead of splitting up the input data, you give each GPU the same input data, but then you split the model. And there are various ways to do this, right? But for example, you could split the gem, which is the core computational pattern in DNN, or you put a layer on a different GPU. But what it means is basically that because every layer needs the outputs from the previous layer, you need to frequently communicate and synchronize, right? Then you go forward pass, backward pass, loss function, update the weights, and repeat. As I said, there are many different ways to do this. So for example, you can split a layer into the gem and then split the gem itself. And if you split it, basically every GPU would calculate a partial sum, and then you would do another all reduce to get the result, right? That's one way. The other way is pipeline parallelism, where you run each layer on a different device, and then you pass on activations or gradients. Generally, it's hard to get good overlap in model parallelism, though. Okay, there's also hybrid parallelism. Of course, since I said the models get really, really large, so they don't really fit into a single GPU's memory. So what they do is they do model parallelism within a box. For example, within a DGX box so with high-speed NVLink, and then they do data parallelism across the InfiniBand fabric. So that's a very common approach to deal with really large models. Okay, so this is basically the background and the introduction. And now I want to go into some research we've been doing, right? And these are my collaborators at Nvidia. And it's basically like moving some of the acceleration into the network. So what can we do to improve the network? And before I do this, I just want to highlight that scaling is important, yes. And there are basically two ways to do this, right? There's weak scaling and strong scaling. So weak scaling would mean we give each GPU a bunch of samples, which is a sub-batch. And then as we add more GPUs, the global batch size would continue to grow, right? Obviously, the upper limit would be the training set. But there's another limit, right? So the left graph shows basically the steps you need to reach the target accuracy when you train, right? So for example, if your batch is just a single sample, you would need number of samples in the training set steps to go through your training set. If you double the batch size, you would only need half the steps. And the idea is if you increase the batch size, it doesn't hurt your training conversions, right? Because you average, but sometimes it even helps. But at some point, if your batch size gets too large, your network doesn't really converge anymore, right? So you either need more epochs or it doesn't converge at all. So there is some upper limit to the global batch. That one's independent, right? So I cannot tell you like, okay, this is 1024. It really depends on the network. So there was a great paper, I think it was by Google, which basically did this study for various networks, right? I just picked two because they are famous, ResNet 50 and Transformer. You can see they behave a little different, right? So ResNet seems to scale better, Transformer like tapers off earlier. And they have different batch sizes, which is the limit, right? And we are interested in like having the minimal training time, right? We want to like train these networks in the shortest amount of time possible. So we need to increase the scale to the maximum, right? And the way to do this, basically, you first pick the maximal batch size that you can afford for conversions. And then you need to figure out the minimum sub-batch size, right? So let's look at the sub-batch size. So what this graph shows, and this is just, yeah, just a plot. There's no like real data here. There's the sub-batch size on the bottom, and then the time on the y-axis. And the gray curve is basically the compute time, right? So as you increase the sub-batch, in the beginning, you don't really notice much difference in the compute time, just because GPUs are already really big processors, right? So you need to have enough work to even utilize one GPU. Of course, this is also DNN dependent. But as you increase it, at some point, you get in this linear region, right? So if you double the amount of work, it basically takes double the amount of time. The communication time is pretty much independent on the sub-batch size, right? It just depends on the model. How many parameters do I have? And the blue one is basically the sum of these two, right? And this graph shows basically I call it low performance network. So what happens if we increase the performance of the network? If we increase the performance and the effective bandwidth, we basically move that yellow curve down, right? And you can see like the blue line basically is linear for a little bit longer, right? This is what we want. So if we pick any point on this graph, right, and we say, okay, this represents n GPUs. We want to train on n GPUs. And we are on the right-hand side of that graph. If we add a more powerful network, double the bandwidth, triple the bandwidth, it doesn't really do much, right? You're still not bottlenecked by the network. So it's the same step time. However, if we want to further decrease the sub-batch size because we want to increase the scale, let's say we go to 4x the number of GPUs, then we are in this left-hand side, in this left region here. And you can see like with a much better network, you get significant speed ups, right? This makes sense. So in other words, if you just look at the slope of this red line here, on the right side, the slope is much steeper. That means we scale better. So this is important. This is why it's important to have high performance network if you want to really like strong scale. I mean, that's not unique to neural networks, right? We do that like in HPC too. Just want to make that clear that how this applies to DNNs. So the research question then is, okay, compute gets faster really, really quickly. The processor of choice for AI today is the GPU, and we want to focus on NVLink, which is a shared memory interconnect. And it's a shared memory interconnect for good reasons, right? GPUs have plenty of memory parallelism, so it makes sense to have a shared memory interconnect. So what can we do to improve bandwidth, latency, and energy? So these are the three metrics we're interested in. The obvious choice, I mean, everything is null reduced, right? In data parallelism, we reduce gradients. In model parallelism, we often reduce partial sums, not always. Again, depends on how you slice and dice it. And in network compute, I mean, it's been shown before. IBM, BlueGene had it. We have it in InfiniBand. However, these solutions really are for not for shared memory systems, right? They're like reservation based. They work with messaging, like RDMA, for example, and they're not really tailored for the GPU. It doesn't really fit with the CUDA model. Today, we have Nickel for this purpose. So Nickel is our communication library that basically works with any system, right? You have NVLink, PCIe, IP, Ethernet. It has collective implementations for all of them. It detects the topology of the system, it optimizes it, and so forth. It has a ring, trees, various algorithms, and it supports SHARP. So SHARP is the in-network all-reduce in InfiniBand. And on the right-hand side, you basically see for like 128 DGX A100 system, the InfiniBand all-reduce performance with and without SHARP, you can see like SHARP improves it by about 2x, right? Which makes sense because in the software algorithm, you usually have a reduction in the broadcast phase, and you only get like 50% of the bandwidth. If you move it into the network, you get 2x. So that shows, okay, network compute seems like a good idea, right? So can we do that for shared memory interconnect? And as always, let's look at what reductions really are, right? Reductions basically follow the reverse path of a multicast tree. So we have a bunch of processors that basically send to one root process, you reduce it, and then you send it out again for the OR reduce, which is the multicast on the right-hand side. So it seems like multicast is a good idea. So let's start with multicast first, right? And in shared memory, a multicast is done the following way, or we propose it to do it this way. There are other ways too. So every GPU has its virtual address space, has a memory allocation that's backed by physical memory. And then we have a separate memory allocation here, which is basically backed by the switch. It's an alias for physical address on multiple GPUs. And if you store to this address, it gets to the switch, right? And the switch port determines, oh, this is actually a multicast address, right? It looks up in the table the targets, and then it multicasts that store to the other GPUs. And once it gets to the GPUs, the local address translation would translate it into a local system address, either physical or virtual, and then you do another physical later. This is a multicast. So the second thing we wanted to do is move the reductions into the network, right? So multicast is only one thing. The reductions are the main thing, right? And actually that works similar, right? Because we also just need to build a tree. What we do is basically we issue a load into the network. That load gets to the first hop switch. And in the first hop switch, we have reduction tables. And we allocate an entry in the reduction table. And then we broadcast or multicast the load request, right? And if you have multiple levels of switches, at the second level, you do the same thing. You get the load, you allocate an entry in the reduction table, you forward the load, and all the GPUs basically respond with their data. That's basically given by the address. That's our naming. Then the response comes back, it gets to the reduction tables, gets reduced, and then the second level reduces it and then sends the partial result back to the first level. And then we return it to the GPU, right? It's from the GPU perspective, that's just a load, right? And the network basically takes care of the rest. And then you multicast the result out if you want to do an all reduce. So this is great. The only problem is you need to synchronize before you do this, right? Because if you don't synchronize, the GPUs aren't in line, right? So one might have updated the address, the other ones might not have, right? So you don't want to fetch stale data, so you need to synchronize. The question is, could we do this without synchronization? And the answer is sure. We just write into the network once we have the data. So instead of a load request, what you do is basically you start just storing the data into the network. So the data gets basically, or the store gets to the port in the first hop switch. And from there, we determine a home port, right? We know, okay, this address needs to be reduced in a certain port. And this makes sure that the data for the same address ends up in the same reduction table. So, okay, so every GPU does the store, and it gets routed to the home port, gets reduced, and gets multicast back out. So this is great. The only problem is that this is actually like a cache, right? Because you never know, you might not have enough resources and you blow out the cache, and then what? So basically the question is then how do you handle misses, right? Capacity misses. So one thing is either you multicast the partials right from the port, and then it's accumulated in the GPUs. So GPUs have L2 atomics, for example, atomic add that's in the L2 cache, so you can leverage that. Or you just send it to one GPU, which is the home GPU, determined by hash function, accumulate it there, and then send it out. So this is how you could handle the misses in the push model. There's still one problem, right? That is not immediately obvious, but if you think about it a little longer, you notice this, which is self-interference in the pull model, for example. So what happens is you do a request, it gets allocated, or it allocates an entry in the reduction buffer. The response comes back, and we multicast it, right? So this works great until we run out of buffers. If we run out of buffers, these requests basically queue up, right? And they queue up back into the GPU. And this is not a problem because responses are on a different VC, so you don't run into deadlocks. However, when the response comes back and we want to multicast the result back out, the multicast gets stuck behind the other reduction requests, unless you add another VC. What that means is that basically multicast and reductions get serialized, and then you lose all your performance benefit. And the push model with the capacity misses, right? As I explained, you can issue the requests, they get reduced, get multicast, and as long as you have enough reduction resources, that's fine. But once you run out, the requests you sent into the network just wasted bandwidth, right? They're not reduced, they're just gonna get turned around, so you wasted bandwidth in your network, and that degrades your performance. And you can simulate that, right? And that's what we did. So for 4 and 16 systems, left is pull model, right is push model, and you can see like the theoretical performance of a Volta GPU in the network. You only achieve half in the pull model, for example. That's because of the self-interference. And in the push model, once you blow out your cache, your performance just goes down. So it's not really worth doing that because you don't get any benefit of doing the reduction in the network. So the way to solve this is basically to do synchronization on a per request basis, right? So you issue some requests, you wait for the response, and then you issue some more. So you limit the number of outstanding requests. And you need to size this appropriately, right? So the number of outstanding requests we call a wave, and then you have multiple of these waves outstanding according to Little's law to make sure that you can hide the synchronization latency. And once you do that, you can see, okay, for the bandwidth, we actually get really close to a speed of light, right? With the push model, and the pull model suffers a little bit if you add in synchronization, but eventually it gets there too. The latency is just better with the push model. And then compared to nickel or the software reductions, you can get a 2x speed up for large messages. This is what you would expect, right? Because you can overlap the multicast and reduction phases. And for smaller messages, you get greater speedups just because you eliminate most of the synchronization. And then what we also did is basically we simulated the networks, the application itself, because sometimes it's great if you can improve the performance of the network by 2x. Sometimes it just doesn't show up in the application. But for example, transformer, so what it shows is blue is Volta 1.1, which basically means a Volta GPU. 2.1 and 4.1 basically assume 2x and 4x higher compute performance, right? That's how we assume future generations of GPUs at the same network bandwidth, because we assume the network bandwidth goes up slower than the compute performance. And then the other two are really like replacing NVLink bandwidth with Ethernet, right? This was, it's interesting, but we won't do that. So we can see basically like with a Volta GPU, you can almost get like 1.5x speed up for like really small batches. And that's what we want, right? We want small batches because you want to scale out. And for the BERT model, it's not so great for Volta, right? Almost no difference here. But as soon as you get a really fast GPU, for example, with our Ampere GPU now, you get great speedups there too. And we did the same for ResNet, which doesn't show much of the speed up that you can expect with these larger models, for example. All right. One thing I want to mention is also the programming model. As I said earlier, the pull model is literally just a load, right? So with Nickel, what you need to do is you have a load store network, right? But then you need to build these like mailbox abstractions, like a send receive. You just store the data into a FIFO. You need a memory fence, which is really expensive. And then you have the flag. With the pull model, for example, it's literally just a load. You load from a reduction region, which is like the special region that's backed by the switch. And then once you get the load back, you multicast it back out, right? And the thread stalls until it has the result. So you don't even need to do anything with synchronization there. And the last thing I want to mention is basically the energy consumption, right? So let's look at the ring algorithm on the left side. So we get 2 stores from the network and 2 stores into memory. It's 2 because we have the 2 phases, the reduction and the broadcast, right? The SM needs to load both of them because they're written to memory. And then for the reduction, it also needs to load what it wants to reduce locally, right? What is added to the whatever is received. And then we store it back out to the next guy. So that's repeated n times because every GPU does it, and n minus 1 times because that's how many steps it takes through the ring. You can add some numbers, and you can argue about the assumptions here, but it doesn't really change fundamentally. And then you get basically this, right? So it's like n squared times 42. I didn't size it, so it gets 32. That was an accident. In network reductions, you basically get the multicast load, and you do your load from the network. And I don't show like load requests or ACKs on the left side for stores. It's just the data bearing packets. And for the memory, we load n times. For the multicast, it's n minus 1 times, and for ourselves, right? And then we do a store, which is a multicast on chip. And then in the network, it gets fanned out, right? So the multiplier is in the network, not on chip. What it comes down to is basically this, right? If we look at the fastest growing term, it's like 42 over 14, which basically means we get a 3x improvement in communication energy. All right, I think I'm almost out of time. So let's conclude. So the conclusion is basically we need to keep scaling, right? Well, we will be counting nodes as we just counted cores before. And you may be able to train in 30 minutes, and you may say, well, 30 minutes is really not a long time. But if you're a data scientist, you really want this to be just a couple of minutes because you want to optimize, you want to play with your model, and you don't want to wait too long to get the results. And both scale up and scale out are important. Network must keep up. And remember, strong scaling is important because we can't increase the batch size infinitely. And for our research results, so we set our research question like, how can we improve the bandwidth, latency, and energy? And I just showed you how we do that. And it fits really well with the GPU's execution model, right? And then the question always is like, how can we improve this even further, right? What are the other communication patterns that we see, and how can we improve them further? Okay, well, thank you very much for first having me today, and I'm happy to take any questions. Thanks.
Great. Thanks a lot, Ben, for the really engaging talk.
Was probably a little bit fast.
I think you're right on time. So,
okay.
Okay. So we can take a few questions from the chat, I guess. So we have a question saying, the data model parallelism design looks like a bootstrap and aggregate model. I'm guessing that's familiar to folks in the HPC community. The question says, the bootstrap aggregate model has bottlenecks in the all-reduce MPI calls for large data bootstraps. Do you have any comments on how to mitigate this all-reduce communication?
So you mean like the setup for the, for example, if you do an MPI all-reduce, right, and InfiniBand, for example, you need to set up the queue pairs and everything. Is that the question?
I feel like the question is asking